We can.
Awesome. Yeah, so I'm going to talk about algorithms in physical Gauss circuits for robots in partially unknown environments. I'm from Dyson School of Design Engineering at Imperial College London. So I'll explain what I mean by Gauss circuits. I think you must have seen this video multiple times. There's a dead trout in a tank, and the difference is there's a water stream starting from the left side, a flow into the right side, and then it is flowing through an obstacle and creating some turbulence. So when the turbulence starts, the dead body starts to swim against the current. So what that means is some of the dynamics needed to swim against the current was in the water, and then the body was just providing another piece of dynamics. And then when they come together, they complete a dynamic circuit that exhibits swimming behavior. So I think at least the foundation of embodied intelligence is in this kind of system of systems coming together in the environment as Gauss circuits, because I call it a Gauss circuit because they are not fixed, they are not hardwired. They just come together when the conditions are right and then dissolve otherwise. For example, if the fish body was stiff, it wouldn't form that circuit. Or if it was too soft like a ribbon, it wouldn't be doing that. So it is just the stiffness distribution and the shape of the body and the vortexes in the environment coming together to form a meaningful circuit to exhibit some useful behavior. So this is not limited to one fish, it can be a school of fish. So it is just that, like, so they have to just position themselves to harness the vortexes created by the first row of fish. So this kind of circuits can be like formed without knowing. So people just agents can tune themselves to local dynamics, and then they can be like knitted together in a bigger fabric of Gauss circuits. So we have explained this thing in more detail in the handbook on soft robotics. It just came out. We'll do a public facing launch on 30th of April. If you search for handbook on soft robotics, meet the authors, share ideas, and explore on Eventbrite, you can find it. So I'll give you some examples of how these Gauss circuits are used in various applications in my lab. So this is one example. So this wheel is just a simple wheel. It doesn't have any sensors or no control at all. It just collides with things, and then the hook emerges, and then it hooks onto those things, and then climbs those obstacles. So the point is, a part of the intelligence was in the morphology, the embodiment of the wheel, and then the other part was on in the environment, right? So these obstacles. So when they come together, they form something meaningful, and then they climb and then do useful things. So it is done without any kind of control. It doesn't have any sensors at all. So this will also be presented in ICRA, and it is also published in RAL. So another example is this mountain goat hoofs, right? So we were thinking about like, so how these mountain goats could survive on those cliffs without slipping, because the brain cannot control if it starts to slip. It doesn't mean that they don't slip at all. So, but they slip, but they autonomously, break again. So if you see this mountain goat inspired hoof versus other types of hooves, what you see is the the rounded hoof would just slip down, or the cube would just slip down, but the mountain goat inspired hoof would like flap on the surface and then basically create something like a ABS type of autonomous braking system. So when you in a vehicle, if you want to brake, Static friction won't break it. So chopping friction allows it to break fast. So this passive emergence of some behavior due to the embodiment of the hoof allows it to chop those friction, normal forces on the surface and then break itself. If somebody thinks that, yeah, it is the edge that does the trick, the cube doesn't do that. So it just bounces its way down the slope. So this was tested in multiple environments. Like, so this is some of my testing at JPL last summer. So these were tested on slopes. So these morphological features of edges, they do help. You saw it is not getting stuck per se. It slips, but it catches again. So this is another camel hoof inspired hoof. So anti-sinking behavior. So if it sinks on sand, it has this autonomous behavior that stops from sinking. So we wanted to understand why camels can be efficient walkers on sand. So this is another example of Yukun Gate's work. So here you can see, so if you try to crunch that weed, this leaf, it can move to one side. So we got this example and then created a capsule, endoscopic capsule. Now we are testing on a colonoscopic capsule. So the idea is like, so when the capsule is soft, it can go to one side, and then the capsule is crunched up, it can go to the opposite side under the same peristaltic waves. So we can use this type of a capsule to autonomously move in the colon and go back and forth and collect more data than a rigid capsule that can just go one pass through the colon or the intestine. So this idea we tested with a sensorized capsule. So when we have four sensors, if there's an anomaly in the tissue, we can capture that um, in four occurrences across the four sensors, and then that gives us some kind of a pattern. And you can see this nodule here was seen here, and then there, and then there. So we can use that as some kind of a particle filter and then locate like early tumor or lesions before it can be seen through a camera. So the advantage of this capsule is like, if it is collapsed, it will go to the opposite side and then it can go back and forth and collect more data. So it is not using any motors or any kind of actuation. It is just harnessing energy from the peristaltic waves. Um, that is pretty similar to that dead fish swimming in the water. Sorry, I'm getting okay. So the last thing um, is this fingertip. This fingertip, we wanted to ask the question, what the fingernail is doing in perception. So this is how to establish a efficient circuit with the environment and then have the right embodiment to perceive better. So we suspected that the curved nature, curved shape of the nail is forming something like a lens that can converge this soft tissue vibrations to a like a low entropy information source for the mechanoreceptors. So we tested with fingers without a bone and a nail, with the nail only without bone, and then only a bone without a nail, and then nail and the bone together. So we suspected that the nail is working like a lens that focuses information, And if so, we should have clearer information with the nail compared to without nail. And then the bone, we suspected that the bone is without the bone, the vibration should be the vector should be 3D, and then it is pointing at different directions. With the bone, it forms a constraint, a mechanical constraint that maps 3D vectors to a 2D manifold because it's a cylindrical constraint. So that should improve the entropy of information. So what we see is with, let's say, without anything, of course, there's no differentiation across different textures. And then with the nail, it increases to, have some differentiation. The bone really helps to differentiate, but like there's a smooth surface, but when you have the nail and the bone together, it has a lot of high differentiation across different textures. So what this means is to establish meaningful Gauss circuits or meaningful dynamic coupling with the texture or the environment, we have to have the right embodiment, the right morphological features in the body. So if all the way going back to the fish example, a fish to be efficient swimmers, they should have the right shape, the right stiffness, the right bones, the right scales, and then the right stiffness distribution from the head to tail. So for the finger, uh, we have to have the nail and we have to have the right morphology of the bone to do texture differentiation. For the capsule, to harness energy from the peristaltic waves, we need to have the capsule morphology that can be just controlled with a meta parameter, which is the relaxed version or the stiff version to go back and forth. So the idea of Gauss circuits is to establish a circuit, you need to have a morphological freedom that can be tuned to establish circuits with the environment and then harness energy or accomplish things that the simple body cannot accomplish on its own. So with that, I will conclude with a group photo we took recently with the Bruce Lee posture on in front of Imperial. Thank you very much.